The Theory That Would Not Die. How Bayes' Rule Cracked the Enigma Code, Hunted Down Russian Submarines, and Emerged Triumphant from 2 Centuries of Controversy. By Sharon Bertsch McGrayne. Narrated by Laural Merlington. Copyright 2011 by Sharon Bertsch McGrayne. This unabridged audiobook is published by arrangement with Yale University Press and was produced in the year 2012 by Tantor Media Incorporated, which holds the copyright thereto. When the facts change, I change my opinion. What do you do, sir? John Maynard Keynes. Preface and note to listeners. In a celebrated example of science gone awry, geologists accumulated the evidence for continental drift in 1912 and then spent 50 years arguing that continents cannot move. The scientific battle over Bayes' rule is less well known but lasted far longer, for 150 years. It concerned a broader and more fundamental issue: how we analyze evidence, change our minds as we get new information, and make rational decisions in the face of uncertainty. And it was not resolved until the dawn of the 21st century. On its face, Bayes' rule is a simple one-line theorem. By updating our initial belief about something with objective new information, we get a new and improved belief. To its adherents, this is an elegant statement about learning from experience. Generations of converts remember experiencing an almost religious epiphany as they fell under the spell of its inner logic. Opponents, meanwhile, regarded Bayes' rule as subjectivity run amok. Bayes' rule began life amid an inflammatory religious controversy in England in the 1740s. Can we make rational conclusions about God based on evidence about the world around us? An amateur mathematician, the Reverend Thomas Bayes, discovered the rule, and we celebrate him today as the iconic father of mathematical decision-making. Yet Bayes consigned his discovery to oblivion. In his time, he was a minor figure, and we know about his work today only because of his friend and editor Richard Price, an almost forgotten hero of the American Revolution. By rights, Bayes' rule should be named for someone else, a Frenchman, Pierre Simon Laplace, one of the most powerful mathematicians and scientists in history. To deal with an unprecedented torrent of data, Laplace discovered the rule on his own in 1774. Over the next 40 years, he developed it into the form we use today. Applying his method, he concluded that a well-established fact, more boys are born than girls, was almost certainly the result of natural law. Only historical convention forces us to call Laplace's discovery Bayes' rule. After Laplace's death, researchers and academics seeking precise and objective answers pronounced his method subjective, dead, and buried. Yet at the very same time, practical problem solvers relied on it to deal with real-world emergencies. One spectacular success occurred during the Second World War, when Alan Turing developed Bayes to break Enigma, the German Navy's secret code, and in the process helped to both save Britain and invent modern electronic computers and software. Other leading mathematical thinkers, Andrei Kolmogorov in Russia and Claude Shannon in New York, also rethought Bayes for wartime decision-making. During the years when ivory tower theorists thought they had rendered Bayes taboo, it helped start workers' compensation insurance in the United States, save the Bell telephone system from the financial panic of 1907, deliver Alfred Dreyfus from a French prison, direct Allied artillery fire and locate German U-boats, and locate earthquake epicenters and deduce, erroneously, that Earth's core consists of molten iron. Theoretically, Bayes' rule was verboten, but it could deal with all kinds of data, whether copious or sparse. During the Cold War, Bayes helped find a missing H-bomb and U.S. and Russian submarines, investigate nuclear power plant safety, predict the shuttle Challenger tragedy, demonstrate that smoking causes lung cancer and that high cholesterol causes heart attacks, predict presidential winners on television's most popular news program, and much more. How could otherwise rational scientists, mathematicians, and statisticians become so obsessed about a theorem that their argument became, as one observer called it, a massive food fight? The answer is simple. At its heart, Bayes runs counter to the deeply held conviction that modern science requires objectivity and precision. Bayes is a measure of belief, and it says that we can learn even from missing and inadequate data, from approximations, and from ignorance. As a result of this profound philosophical disagreement, Bayes' rule is a flesh-and-blood story about a small group of beleaguered believers who struggled for legitimacy and acceptance for most of the 20th century. It's about how the rule's fate got entwined with the secrecy of the Second World War and the Cold War. It's about a theorem in want of a computer and a software package. And it's about a method that, refreshed by outsiders from physics, computer science, and artificial intelligence, was adopted almost overnight because suddenly it worked. In a new kind of paradigm shift for a pragmatic world, the man who had called Bayes the crack cocaine of statistics, seductive, addictive, and ultimately destructive, began recruiting Bayesians for Google. Today, Bayesian spam filters whisk pornographic and fraudulent email to our computers' junk bins. When a ship sinks, the Coast Guard calls on Bayes and locates shipwrecked survivors who may have floated at sea for weeks. Scientists discover how genes are controlled and regulated. Bayes even wins Nobel Prizes. Online, Bayes' rule trolls the web and sells songs and films. It has penetrated computer science, artificial intelligence, machine learning, Wall Street, astronomy and physics, Homeland Security, Microsoft, and Google. It helps computers translate one language into another, tearing down the world's millennia-old Tower of Babel. It has become a metaphor for how our brains learn and function. Prominent Bayesians even advise government agencies on energy, education, and research. But Bayes' rule is not just an obscure scientific controversy laid to rest. It affects us all. It's a logic for reasoning about the broad spectrum of life that lies in the gray areas between absolute truth and total uncertainty. We often have information about only a small part of what we wonder about, yet we all want to predict something based on our past experiences. We change our beliefs as we acquire new information. After suffering years of passionate scorn, Bayes has provided a way of thinking rationally about the world around us. This is the story of how that remarkable transformation took place. Note: observant listeners may notice that I use the word probability a lot in this book. In common speech, most of us treat the words probability, likelihood, and odds interchangeably. In statistics, however, these terms are not synonymous. They have distinct and technical meanings. Because I've tried to use correct terminology in the theory that would not die, probability appears quite a bit. Part 1. Enlightenment and the Anti-Bayesian Reaction. 1. Causes in the air. Sometime during the 1740s, the Reverend Thomas Bayes made the ingenious discovery that bears his name but then mysteriously abandoned it. It was rediscovered independently by a different and far more renowned man, Pierre Simon Laplace, who gave it its modern mathematical form and scientific application, and then moved on to other methods. Although Bayes' rule drew the attention of the greatest statisticians of the 20th century, some of them vilified both the method and its adherents, crushed it, and declared it dead. Yet at the same time it solved practical questions that were unanswerable by any other means. The defenders of Captain Dreyfus used it to demonstrate his innocence. Insurance actuaries used it to set rates. Alan Turing used it to decode the German Enigma cipher and arguably save the Allies from losing the Second World War. The U.S. Navy used it to search for a missing H-bomb and to locate Soviet subs. Rand Corporation used it to assess the likelihood of a nuclear accident. And Harvard and Chicago researchers used it to verify the authorship of the Federalist Papers. In discovering its value for science, many supporters underwent a near-religious conversion, yet had to conceal their use of Bayes' rule and pretend they employed something else. It was not until the 21st century that the method lost its stigma and was widely and enthusiastically embraced. The story began with a simple thought experiment. Because Bayes' gravestone says he died in 1761 at the age of 59, we know he lived during England's struggle to recover from nearly 2 centuries of religious strife, civil war, and regicide. As a member of the Presbyterian Church, a religious denomination persecuted for refusing to support the Church of England, he was considered a dissenter or nonconformist saint during his grandfather's generation. 2,000 dissenters died in English prisons. By Bayes' time, mathematics was split along religious and political lines, and many productive mathematicians were amateurs because, as dissenters, they were barred from English universities. Unable to earn a degree in England, Bayes studied theology and presumably mathematics at the University of Edinburgh in Presbyterian Scotland, where, happily for him, academic standards were much more rigorous. In 1711 he left for London, where his clergyman father ordained him and apparently employed him as an assistant minister. Persecution turned many English dissenters into feisty critics, and in his late 20s Bayes took a stand on a hot theological issue. Can the presence of evil be reconciled with God's presumed beneficence? In 1731 he wrote a pamphlet, a kind of blog, declaring that God gives people the greatest happiness of which they are capable. During his 40s, Bayes' interests in mathematics and theology began to tightly intertwine. An Irish Anglican bishop, George Berkeley, for whom the University of California's flagship campus is named, published an inflammatory pamphlet attacking dissenting mathematicians, calculus, abstract mathematics, the revered Isaac Newton, and all other free thinkers and infidel mathematicians who believed that reason could illuminate any subject. Berkeley's pamphlet was the most spectacular event in British mathematics during the 1700s. Leaping into the pamphlet wars again, Bayes published a piece defending and explaining Newton's calculus. This was his only mathematical publication during his lifetime. Shortly thereafter, in 1742, 5 men, including a close friend of Newton's, nominated Bayes for membership in the Royal Society. His nomination avoided any hint of controversy and described him as a gentleman of known merit, well skilled in geometry and all parts of mathematical and philosophical learning. The Royal Society was not the professional organization it is today. It was a private organization of dues-paying amateurs from the landed gentry. But it played a vital role, because amateurs would produce some of the era's breakthroughs. About this time, Bayes joined a second group of up-to-date amateur mathematicians. He had moved to a small congregation in a fashionable resort, the cold water spa Tunbridge Wells. As an independently wealthy bachelor, his family had made a fortune manufacturing Sheffield steel cutlery. He rented rooms, apparently from a dissenting family. His religious duties, 1 Sunday sermon a week, were light. And spa etiquette permitted dissenters, Jews, Roman Catholics, and even foreigners to mix with English society, even with wealthy earls, as they could not elsewhere. A frequent visitor to Tunbridge Wells, Philip, the second Earl of Stanhope, had been passionately interested in mathematics since childhood, but his guardian had banned its study as insufficiently genteel. When Stanhope was 20 and free to do as he liked, he seldom raised his eyes from Euclid. According to the blue-stocking Elizabeth Montagu, Stanhope was always making mathematical scratches in his pocket-book, so that one half the people took him for a conjurer and the other half for a fool. Because of either his aristocratic position or his late start, Stanhope never published anything of his own. Instead, he became England's foremost patron of mathematicians. The Earl and the Royal Society's energetic secretary, John Canton, operated an informal network of peer reviewers who critiqued one another's work. At some point, Bayes joined the network. One day, for example, Stanhope sent Bayes a copy of a draft paper by a mathematician named Patrick Murdoch. Bayes disagreed with some of it and sent his comments back to Stanhope, who forwarded them to Murdoch, who in turn replied through Stanhope, and so on around and around. The relationship between the young Earl and the older Reverend Bayes seems to have ripened into friendship, however, because Stanhope paid Bayes at least one personal visit at Tunbridge Wells, saved 2 bundles of his mathematical papers in the Stanhope Estates library, and even subscribed to his series of sermons. Another incendiary mix of religion and mathematics exploded over England in 1748, when the Scottish philosopher David Hume published an essay attacking some of Christianity's fundamental narratives. Hume believed that we can't be absolutely certain about anything that is based only on traditional beliefs, testimony, habitual relationships, or cause and effect. In short, we can rely only on what we learn from experience. Because God was regarded as the first cause of everything, Hume's skepticism about cause and effect relationships was especially unsettling. Hume argued that certain objects are constantly associated with each other. But the fact that umbrellas and rain appear together does not mean that umbrellas cause rain. The fact that the sun has risen thousands of times does not guarantee that it will do so the next day. And most important, the design of the world does not prove the existence of a creator, an ultimate cause. Because we can seldom be certain that a particular cause will have a particular effect, we must be content with finding only probable causes and probable effects. In criticizing concepts about cause and effect, Hume was undermining Christianity's core beliefs. Hume's essay was non-mathematical, but it had profound scientific implications. Many mathematicians and scientists believed fervently that natural laws did indeed prove the existence of God, their first cause. As an eminent mathematician, Abraham de Moivre wrote in his influential book Doctrine of Chances, calculations about natural events would eventually reveal the underlying order of the universe and its exquisite wisdom and design. With Hume's doubts about cause and effect swirling about, Bayes began to consider ways to treat the issue mathematically. Today, probability, the mathematics of uncertainty, would be the obvious tool. But during the early 1700s, probability barely existed. Its only extensive application was to gambling, where it dealt with such basic issues as the odds of getting 4 aces in one poker hand. De Moivre, who had spent several years in French prisons because he was a Protestant, had already solved that problem by working from cause to effect. But no one had figured out how to turn his work around backward, to ask the so-called inverse question from effect to cause. What if a poker player deals himself 4 aces in each of 3 consecutive hands? What is the underlying chance, or cause, that his deck is loaded? We don't know precisely what piqued Bayes' interest in the inverse probability problem. He had read de Moivre's book, and the Earl of Stanhope was interested in probability as it applied to gambling. Alternatively, it could have been the broad issues raised by Newton's theory of gravitation. Newton, who had died 20 years before, had stressed the importance of relying on observations, developed his theory of gravitation to explain them, and then used his theory to predict new observations. But Newton had not explained the cause of gravity or wrestled with the problem of how true his theory might be. Finally, Bayes' interest may have been stimulated by Hume's philosophical essay. In any event, problems involving cause and effect and uncertainty filled the air, and Bayes set out to deal with them quantitatively. Crystallizing the essence of the inverse probability problem in his mind, Bayes decided that his goal was to learn the approximate probability of a future event he knew nothing about except its past, that is, the number of times it had occurred or failed to occur. To quantify the problem, he needed a number, and sometime between 1746 and 1749, he hit on an ingenious solution. As a starting point, he would simply invent a number. He called it a guess, and refine it later as he gathered more information. Next, he devised a thought experiment, a 1700s version of a computer simulation. Stripping the problem to its basics, Bayes imagined a square table so level that a ball thrown on it would have the same chance of landing on one spot as on any other. Subsequent generations would call his construction a billiard table, but as a dissenting minister, Bayes would have disapproved of such games, and his experiment did not involve balls bouncing off table edges or colliding with one another. As he envisioned it, a ball rolled randomly on the table could stop with equal probability anywhere. We can imagine him sitting with his back to the table so he cannot see anything on it. On a piece of paper he draws a square to represent the surface of the table. He begins by having an associate toss an imaginary cue ball onto the pretend tabletop. Because his back is turned, Bayes does not know where the cue ball has landed. Next we picture him asking his colleague to throw a second ball onto the table and report whether it landed to the right or left of the cue ball. If to the left, Bayes realizes that the cue ball is more likely to sit toward the right side of the table. Again Bayes's friend throws the ball and reports only whether it lands to the right or left of the cue ball. If to the right, Bayes realizes that the cue can't be on the far right-hand edge of the table. He asks his colleague to make throw after throw after throw. Gamblers and mathematicians already knew that the more times they tossed a coin, the more trustworthy their conclusions would be. What Bayes discovered is that, as more and more balls were thrown, each new piece of information made his imaginary cue ball wobble back and forth within a more limited area. As an extreme case, if all the subsequent tosses fell to the right of the first ball, Bayes would have to conclude that it probably sat on the far left-hand margin of his table. By contrast, if all the tosses landed to the left of the first ball, it probably sat on the far right. Eventually, given enough tosses of the ball, Bayes could narrow the range of places where the cue ball was apt to be. Bayes's genius was to take the idea of narrowing down the range of positions for the cue ball and, based on this meager information, infer that it had landed somewhere between two bounds. This approach could not produce a right answer. Bayes could never know precisely where the cue ball landed, but he could tell with increasing confidence that it was most probably within a particular range. Bayes's simple, limited system thus moved from observations about the world back to their probable origin or cause. Using his knowledge of the present, the left and right positions of the tossed balls, Bayes had figured out how to say something about the past, the position of the first ball. He could even judge how confident he could be about his conclusion. Conceptually, Bayes's system was simple. We modify our opinions with objective information. Initial beliefs, our guess where the cue ball landed, plus recent objective data, whether the most recent ball landed to the left or right of our original guess, equals a new and improved belief. Eventually names were assigned to each part of his method: prior for the probability of the initial belief, likelihood for the probability of other hypotheses with objective new data, and posterior for the probability of the newly revised belief. Each time the system is recalculated, the posterior becomes the prior of the new iteration. It was an evolving system, which each new bit of information pushed closer and closer to certitude. In short, prior times likelihood is proportional to the posterior. In the more technical language of the statistician, the likelihood is the probability of competing hypotheses for the fixed data that have been observed. However, Andrew Dale, a South African historian of statistics, simplified the matter considerably when he observed, put somewhat rudely, the likelihood is what remains of Bayes's theorem once the prior is removed from the discussion. As a special case about balls thrown randomly on a flat table, Bayes's rule is uncontroversial. But Bayes wanted to cover every case involving uncertainty, even cases where nothing whatsoever was known about their history. In his words, where we absolutely know nothing antecedently to any trials. This expansion of his table experiment to cover any uncertain situation would trigger 150 years of misunderstanding and bitter attacks. Two especially popular targets for attack were Bayes' guesswork and his suggested shortcut. First, Bayes guessed the likely value of his initial belief, the cue ball's position, later known as the prior. In his own words, he decided to make a guess whereabouts its probability is, and then see the chance that the guess is right. Future critics would be horrified at the idea of using a mere hunch, a subjective belief, in objective and rigorous mathematics. Even worse, Bayes added that if he did not know enough to distinguish the position of the balls on his table, he would assume they were equally likely to fall anywhere on it. Assuming equal probabilities was a pragmatic approach for dealing with uncertain circumstances. The practice was rooted in traditional Christianity and the Roman Catholic Church's ban on usury. In uncertain situations such as annuities or marine insurance policies, all parties were assigned equal shares and divided profits equally. Even prominent mathematicians assigned equal probabilities to gambling odds by assuming, with a remarkable lack of realism, that all tennis players or fighting cocks were equally skillful. In time, the practice of assigning equal probabilities acquired a number of names, including equal priors, equal a prioris, equal probability, uniform distribution probability, and the law of insufficient reason, meaning that without enough data to assign specific probabilities, equal ones would suffice. Despite their venerable history, equal probabilities would become a lightning rod for complaints that Bayes was quantifying ignorance. Today, some historians try to absolve him by saying he may have applied equal probabilities to his data, the subsequent throws, rather than to the initial so-called prior toss. But this is also guesswork, and for many working statisticians, the question is irrelevant, because in the tightly circumscribed case of balls that can roll anywhere on a carefully leveled surface, both produce the same mathematical results. Whatever Bayes meant, the damage was done. For years to come, the message seemed clear. Priors be damned. At this point, Bayes ended his discussion. He may have mentioned his discovery to others. In 1749, someone told a physician named David Hartley something that sounds suspiciously like Bayes' rule. Hartley was a Royal Society member who believed in cause and effect relationships. In 1749, he wrote that an ingenious friend has communicated to me a solution of the inverse problem, which shows that we may hope to determine the proportions and by degrees the whole nature of unknown causes by a sufficient observation of their effects. Who was this ingenious friend? Modern-day sleuths have suggested Bayes or Stanhope, and in 1999 Stephen M. Stiegler of the University of Chicago suggested that Nicholas Saunderson, a blind Cambridge mathematician, made the discovery instead of Bayes. No matter who talked about it, it seems highly unlikely that anyone other than Bayes made the breakthrough. Hartley used terminology that is almost identical to Bayes' published essay, and no one who read the article between its publication in 1764 and 1999 doubted Bayes' authorship. If there had been any question about the author's identity, it is hard to imagine Bayes' editor or his publisher not saying something publicly. 30 years later, Price was still referring to the work as that of Thomas Bayes. Although Bayes' idea was discussed in Royal Society circles, he himself seems not to have believed in it. Instead of sending it off to the Royal Society for publication, he buried it among his papers, where it sat for roughly a decade. Only because he filed it between memoranda dated 1746 and 1749 can we conclude that he achieved his breakthrough sometime during the late 1740s, perhaps shortly after the publication of Hume's essay in 1748. Bayes' reason for suppressing his essay can hardly have been fear of controversy. He had plunged twice into Britain's pamphlet wars. Perhaps he thought his discovery was useless. But if a pious clergyman like Bayes thought his work could prove the existence of God, surely he would have published it. Some thought Bayes was too modest, and others wondered whether he was unsure about his mathematics. Whatever the reason,
Sample complete. Ready to continue?